Welcome to Elements of Astronomy. In this course, we will be taking a look at the universe as a whole. Our very first unit is Exploring the Sky, of which Chapter 1, Here and Now, is a part of. And so in this course, yes, we're going to be taking a look at scale. So scale is going to be on the terms that we don't ordinarily think of. Different sizes, different distances, and time scales than what we're used to thinking about. We kind of, our experiences are more or less medium as far as scale goes. A human lifetime, a few miles, 100 miles, which we can kind of wrap our minds around. But when we talk about the field of astronomy, those scales become actually microscopic to astronomical. And so we will be looking at in this chapter this idea of scale and different units that we use. Astronomers have even come up with new units to express distances because they become so large in sizes. So we'll be exploring that. In the backs of the chapters, there's always these little summaries of what are we, kind of summaries. And today's chapter 1 is we are participants. We live in the universe, and we are very much a part of the universe. So astronomy is the study of stars, but it is also very much about you. So that should be a take away kind of a theme here, that astronomy is about you. Okay, so chapter 1 here, the here and now. So it's more than just the study of planets, which we'll look at in closer detail. Stars, we will actually have a star unit that we'll look at, and galaxies. We'll have a galaxy unit as well. So it's more than just that. It is the study of the whole universe in which you live. You are very much a big part of the universe. And so like I mentioned, it's going to introduce us to sizes and distances and even time scales beyond our usual Earth experiences. And so we're going to try to get a grasp on these unfamiliar sizes, distances, and even time as we go through the semester. But scale, as I mentioned before, is very important to get a handle on. All right, so we're going to be comparing sizes of objects of different sizes to comprehend the scale of the universe. So they're going to kind of take us through, kind of like a cosmic zoom as we continue to kind of back our way out and get a larger and larger view of the universe. And so kind of right here, here's some scale. Let's say the sun compared to the earth. Okay, so the sun's pretty large, right, in comparison to the earth that we live on, and we think, yeah, the earth is pretty big. But in comparison to our star, our closest star, the sun, pretty tiny. Okay, and we're going to find that our star, the sun, is actually pretty small in the world of stars. Okay, so scale here. All right, so each picture that we're going to look at is going to increase our field of view by 100 times wider than the preceding picture. So we're going to kind of go on the little cosmic zoom here as we go through. So starting off, we're looking at here a person, sitting out here on a park bench. So we see a sidewalk. We can kind of relate to that. Sky view, trees, okay, kind of up high, maybe if you're on several floors up in a building, this might be a view that you are familiar with. But we've got just 16 meters across in our field of view here, so about 52 feet they're mentioning in that field of view. And so now here we're increasing that by a factor of 100. This one, this is where that little park bench would have been that person was sitting on. And now this is looking at maybe an aerial view up in an airplane. If you've ever been in an airplane and seen that view, this might be something you would see from an airplane. Now this time we're seeing the whole campus, the college campus, in this view, streets and houses around it. So we can still probably relate to that one. Here, this one's interesting in that, yeah, it's spanning 100 miles here, but the coloration on this is sort of color-coded. It's using infrared, so that term infrared is part of our electromagnetic spectrum. So not just visible light, which is just one portion of the electromagnetic spectrum, but in astronomy we're going to learn that astronomers have a need to use the entire electromagnetic spectrum, from the very, very small X-rays, gamma rays, even to the very long, longer infrared and microwave and radio waves as well. So they use the entire electromagnetic spectrum to gather information to help us to study the universe, not just visible light. Okay, that limits us quite a bit if we stick with that. So this has sort of been infrared, so our eyes, really only see in the visible light range. So they've kind of color-coded this it's called false coloration. But this is the Susquehanna River, okay, in southern Pennsylvania. You see a few little white puffy things there. That's part of our atmosphere, the clouds of our atmosphere in there. So this little one, just a higher up field where we're taking a look at the river running through the Allegheny Mountains there on our eastern kind of coast area. Here we go. So we're broadening that again. Now we're up to 8,000 miles in diameter. So we see the big, beautiful Earth, planet Earth, Mother Earth. The blue planet, it is strikingly blue from outer space. You see that? Our planet is majority covered in ocean, about 70%, 71% of the surface of the Earth is covered in ocean. And so you do see strikingly that we are the blue planet. And then you also see the little swirly white. This does show the atmosphere, the very important atmosphere that we depend on. Our lives do depend on that very thin mixture of gases in the atmosphere. It's very thin envelope of gases that surrounds our planet, but our lives do depend on that atmosphere. And we'll be comparing in our planetology, when we study the other planets, comparisons of what the planets look like without an atmosphere, or with very, very thick atmospheres. And so some differences. We're kind of in that Goldilocks zone where it's just right for living organisms to thrive here. Okay, so now we're backing it up again. So we're getting a little larger view, factor of 100 here. So now we're at about 1 million miles wide, okay, here. So here's the Earth, little blue dot at the center. And now we see our satellite, the moon, okay, which does orbit around the Earth, and it's about 1/4 the diameter of the Earth, but it's our only satellite that we do have, okay, in that view. And then they've kind of done a little Earth versus moon enlarged for relative size. Okay, so next then, so planets is one thing. I'm going to kind of write up a hierarchy here for scale. This will be our scale. Just to get a feel for what's small versus large on this universe type of a scale here within the universe. So Planets would be down on the small end of the scale. Okay, now planets do not generate their own energy. Okay, so they just have reflected light. So when we look in the night sky and we see planets like Jupiter or Saturn or various others, why they look bright to us is because that is reflected light from the sun. They're not generating their own light. Okay, planets don't generate their own light. Stars do. Okay, so here we are. We're backing that out again, a factor of 100. Earth and its moon, right here, the small kind of little red box. Okay, so the Earth and Sun relative there. So that would be there now. And we see Venus here, Mercury here, so the inner two planets closest into the Sun. But this is part of the solar system. Okay, the Sun and its family of planets, and some other small bodies we call satellites, so the moons around other planets, asteroids, leftover rocky material from when the solar system was forming, some leftover material, comets, leftover material when the icy planets were forming. So sort of the space debris, they call that, leftover material. So what we're seeing here then is the sun at the center, and we can only see 3 planets in this view, okay? But solar system would be kind of next in our scale here. Okay, so planets are smaller end, solar system larger, okay? And then let's go out again, another one here. Oh, well, here they're defining some things. The planet, small, non-luminous, okay, bodies. And so these don't produce their own energy, their own light. So they're bright, they shine because of reflected light, as I mentioned before. But a star is a self-luminous ball of hot gases that does emit its own energy, its own light. Okay, so kind of a difference between a planet and a star. Okay, kind of taking a little break from the cosmic zoom here to interject this about astronomy is a science of big numbers, and actually very, very small numbers as well when we start talking about the electromagnetic spectrum and some of those waves and frequencies that are very, very small, and the atoms and things like that, but very, very large as well, okay? And so sometimes these units that we use, kilometers and miles, they're just not enough for us. When we start getting those very, very large distances, say between planets, from the sun to the planet, miles, kilometers even become very cumbersome with all the zeros that you have to put on there. So something like the average distance of the Earth to the moon kind of thing, 380,000 kilometers or 240,000 miles. This just gets very cumbersome. So rather than kind of writing out all those zeros, we have a method here of using scientific notation. Really helps us simplify our numbers. So I have a few examples, even a few more than what they have. They just give you one example. I'm going to give you a few more to make sure we can handle scientific notation. So for example, they have that number 380,000. Well, for scientific notation, you want to put that in what we call unity, meaning there's only one digit before your decimal point, okay? And so one digit before the decimal point, okay? And then you'll base that on the number of zeros to get your multiplier, to get your power of 10, okay, factor in there. So let's just take a look at some of this. Get get that over on the camera here. Okay, if that will stay still for us. Okay, so we're expressing the number as unity multiplied by the correct power of 10. So unity means one digit in front of the decimal point, okay? And the number of decimal places that get moved gives the exponent for the power of 10. So 10 to the whatever number, okay? If we end up, if the decimal is moved to the left, okay, the power of 10 becomes a positive number. If, however, the decimal is moved to the right, that power of 10 becomes negative, a negative number. Okay, so 380,000 is written as, here's unity, okay, one place before the decimal, so the 3.8. Now, how many times 10 to the what number? What's that going to be, the multiplier there? Count your zeros or your places over. So 1, 2, 3, 4, 5. In order to achieve unity, we had to move the decimal point 5 places, and we went to the left, right? So 1, 2, 3, 4, 5. So we put times 10 to the 5th power, okay, with that. So that equals the 3.8 times that multiplier, which is 10 to the 5th, which is 100,000, and that's going to give you your value of that number in scientific notation. So it really is a nice way to simplify all these cumbersome numbers that we can end up encountering in astronomy, okay, our study of the universe, these various large sizes. I mean, these numbers can be small too. This one here, let's pull that down now. Get that on there. Just for good measure, so that I can make sure that you do have a handle on this and could do this, say, for example, on the exam. So for this one, we've got just the number 365, okay? 365 days in the year, something like that. But if we wanted to convert that to scientific notation, okay, you get it in unity, you want one digit in front of your decimal point, okay? So we ended up having to move the decimal 1, 2 to the left, okay? And so that becomes our power of 10 times 10 to the 2nd, okay, in there. And that ends up giving us our correct expression, 100, right? 3.65 times 100 is 365. So this is scientific notation. We'll keep it going with a few more problems. Well, let's go the other way with it. Let's say we've got it in scientific notation, and then we want to write it in normal notation, the longhand way of writing it. So let's be able to go both ways with this. So say we have 1.5 times 10 to the 7th. Okay, what would that be? So 1.5, and then from that decimal point, we would go to the right 7 times, because it's a positive number. 1, 2, 3, 4, 5, 6, and 7. So 1, 2, 3, 4, 5, 6, and 7. So that becomes 15 million. Okay, so in a million, you've got 6 zeros, right? So 15 million was this one. So we kind of went the other way with it. Took it from scientific notation and put it back into normal notation. Be able to do both. Okay. Here we go. Here's just one, whoops, with the number billion. I want you to be able to see that too. Getting a feel for what a billion is, and billion's got like 9 places in it. So 4.25 billion, 9 places for billion. So you would want to go over 9 places. So 4.25 times 10 to the 9th, okay, which, you know, if you wrote it out longhand, you're going over 9 places. 1, 2, 3, 4, 5, 6, 7, 8, and 9. 9 places for billion. So if I gave you just the words billion, know that that has 9 places. If I gave you the word million, know that that has 6 places, okay? A little something to help you with some numbers there. Okay, what do we got next here? Example 5. So here we have a very small number, and we want to write this in scientific notation. So it's 0.0073. Again, you need to get it into unity to where your decimal point has 1 digit in front of it, just 1 digit in front of it. It's called unity. So we want to get that decimal put right to there. And so to achieve that, we had to move our decimal point 1, 2, 3 places, but 3 places to the right. And so when you move that decimal point to the right, you'll have a negative, okay, integer up there, okay, a negative multiplier. So this would become 7.3 times 10 to the minus 3. Okay, so the correct multiplier is 0.001 or 10 to the minus 3. Okay, so now we're going the other way. So that's very small. When you see a negative number like that, that's a small number. Positive number is a large number. Okay, so that the zeros before the 7 are not included when you convert that to scientific notation. Okay, unity is just 1. Okay, let's see, I've got one more on here. So again, this is a small number in there, and we want to get it into unity, so 1 place before the decimal point. So we end up going 1, 2, 3, 4, 5 places, but to the right, and so it is a minus 5. Okay, on that, our multiplier is a minus 5. We went 5 places to the right. And so we would use 5.01 times 10 to the minus 5. And in this case, that 0 between the 5 and the 1, it is an important place value for getting the correct value of the number. You wouldn't just want to leave that out. Okay. So these were just a few examples to make sure that you can do some conversions on the exam. That is one of your bullets of things to know from this chapter, which incidentally is right here. Okay. This is part of your study guide for the first exam, and I've got all the chapters that are going to be on that, but up towards the top here, okay, we want to be able to write numbers in scientific notation. That's kind of like our first bullet on there. Second bullet, understand the hierarchy to the scale of the cosmos. So which things are small, which things are large. Well, we're getting there. We haven't quite got through our list yet, but we're getting there for that. No units of distance in astronomy. So we're getting to those as well. And be able to perform conversions, okay, unit conversion, which we will touch upon those here in just a bit. Okay, but that was a little bit with the first bullet on your study guide, making sure that you can get a grip on the scientific notation conversions, okay? Being able to use that. Okay. All right, so let's keep going here then. Okay, so now here's some units that they're starting to throw our way. The large numbers. Yes, astronomers do have new units of measurement because the distances and the sizes that they encounter become so large that our, kilometers don't cut it, miles don't cut it. So we start to use some units, and they're introducing to us the astronomical unit. So AU, the astronomical unit. important unit. Equivalent to, they've got a couple things here, 1.5 times 10 to the 8 kilometers, so that's in kilometers, or 93 million miles. That's a large number, 93 million miles, and 1.5 times 10 to the 8, right, kilometers. So that's a very large numbers in there. So what they do is the astronomical unit is that average distance between the Earth and the Sun. So they use the Sun and the distance to the Earth on average, because the Earth does, as it goes in its orbit around the Sun, sometimes it's a little closer, sometimes it's a little farther away in its orbit, but they're taking the average, okay, of that. So the average distance from the Earth to the Sun, that's known as an astronomical unit. So we can just maybe write that out, 1.5 times 10 to the 8 in kilometers, if we were to use that, or 93 million miles in there. Okay. So that's what the Earth is. The Earth's distance from the Sun is 1 AU, they say. Abbreviate that AU, astronomical unit. That's a very important unit in astronomy. Let's see, I don't know that they're going to introduce everything. Yeah, they might here. The light year, I think, is coming up. So, okay, so we'll add another one to that list here in a minute. So here we go. We're enlarging by another factor of 100 in our view. So here we're seeing the entire solar system, Sun at the center, right? You're starting to see all kind of jam-packed in there. Mars, but towards the center, because those distances are getting really small from the Sun, they're kind of all crowded. Mercury, Venus, and Earth are all kind of crowded right in there around the Sun, so they're lying really close together that you can't really separate them on this much larger scale here. Mars is the next one out, which is 1.5 AU from the Sun. So the Earth is 1 AU from the Sun, and Mars is another half of an AU away from the Sun. So a 1.5 AU from the Sun, okay, is where Mars is, okay? And then these are a little further out, and then we start to get like 5 AU, 10 AU, 20, and so on, 30 AU. And then Pluto's onwards out there at about 50 AU away from the Sun, almost 50. Way out there. So see how the AU really helps us instead of having to say, oh, 1 times 20, 30, 40, 50 kilometers times 10 to the 50 kilometers. I mean, very cumbersome that way. But by introducing the astronomical unit, it's good for some of these distances, especially between, say, planets. It's a good one. Okay. Yeah, and so then Pluto, they're talking about little Pluto out here, orbits mostly outside of Neptune, but it's not considered a major planet anymore, to the dismay of many people. But Pluto has been reclassified as a dwarf planet, and we'll have much more to say about Pluto in our solar system unit a little later on. Right, so here we are, enlarging the field by another factor of 100. And so now all we're seeing is the Sun, our star in our solar system. And so you really can't distinguish the planets that are orbiting around it in this view, okay? Everything's kind of crowded into a small little square around our star. Notice also in this view that we don't see any other stars. So distances between stars are even larger, okay, than, you know, it almost gets to a point that the astronomical unit is no longer useful for us when we think about this. But this particular view has a diameter here of 11,000 AU. So we don't have any stars even within 11,000 AU. Not really near us at all. Okay, here we go again. So now we're expanding our view again. Here we have a diameter a bit over 1 million AU. astronomical units. So we got the sun at the center, and now these dots here are other stars, okay? So they're really far away to the point that giving their distances in AU becomes unreasonable. It's really not reasonable to talk about AUs even. And so astronomers have come up with an even larger unit of measurement, the light year, okay? So there you are, the light year. Okay, so this is the distance that light travels in 1 year, the light year. Okay, and they give us some things here. We could put it in kilometers if you wanted to, 10 to the 13 kilometers. Or what might help us make a little more sense, because we just kind of mastered the astronomical unit, is that it is 63,000 AU. So a light year is 63,000 AU. So if 1 AU is the distance between the Earth and the Sun, average distance, that's 1 AU. A light year is 63,000 AU. So a much larger unit of measurement. And now this becomes a little bit better way to start talking about distances between stars. Let's say so many light years away. Okay, that becomes the better, more reasonable unit to use. So like I mentioned, astronomers do have some new units that they do introduce for us. And so this field of view is 17 light years, okay? And so we've got a few stars in our view. The nearest star to our star, the sun, is Proxima Centauri, and it is 4.2 light years away. So go 4.2 times 63,000 AU, that's a long ways away, okay? It takes 4.2 years. The light from Proxima Centauri takes 4.2 years, okay, to make it to the Earth. So a light year, yeah, in there. So that does help us with these very large distances. They're mentioning in here about the different sizes of the dots, okay? It doesn't really have anything to do with the size of the star. It just has something to do with the brightness of the stars. And when we go into our star unit a little later, we're going to see why that's important. It's how they're imaged when in a photo. The very bright ones seem to look a little bit larger. Really doesn't have anything to do with the star size, but it has to do with their brightness. Okay. One other unit that I want to add that they don't mention in this chapter 1, but that I'll just introduce it now, is the parsec, and it's an even larger unit than the light year. So a parsec, PC for parsec. I don't think they define that for you, so I might go ahead and write that down. Put up a few things here. I put in a few things. So a parsec, okay, that's a distance at which a star must lie okay, in order for its measured parallax to be exactly 1 arc second. And so when we're talking about these arc seconds, that is a fraction of a degree of an angle. Okay, it has really nothing to do with time, but a degree, and then there's a fraction of a degree we call an arc minute, and then there's a fraction of an arc minute that's called an arc second. Okay, and so we want the measured parallax, and the parallax is the kind of apparent motion of an object that's really due to the motion of the observer. So for example, if we were to put our thumb, straight out in front of us, we don't move the thumb. But let's say we close one eye. I'm going to close this eye and I'm looking at my thumb. You might try this at home. And then I open my eye and close the other eye and go back and forth, back and forth. It looks like my thumb is moving, but I didn't move my thumb. But it looks like, because of the position of the observer, my eyes, they're set a little apart. And I'm looking, switching eyes there. It looks like my thumb is moving. And how much of a degree of angle is it moving? That's the parallax, okay? And so this is saying the distance at which a star must be, how far away it must be, in order for its measured parallax to be 1 arc second. It's kind of a cumbersome thing there, definition for a parsec though. But a parsec, if we wanted that in kilometers, 3 times 10 to the 13th, okay, a big number there. 3.1 times 10 to the 13th kilometers, or 206,000 AU. Okay, so we have an AU and it's 206,000 of those, distance between the Earth and the Sun, or 3.3 light years, if you like that better. Okay, light years, 3.3 light years is a parsec, so an even larger unit of distance that I'm introducing now. It'll become important a little later on. They didn't mention it in this chapter though, but it doesn't hurt to put that one in there. It's even a little bit larger. Okay. And then a kiloparsec, I mean, you can put prefixes in front of here, like we put kilometer, wherever the kilometer is, there's a meter, and then there's a kilometer. You could say a kiloparsec, so 1,000 parsecs is a kilo parsec. So yeah, you can put prefixes in front of these units like we do other units as well. Okay, so these are some units, and we'll be doing some conversions, so we have some good values there to be able to do some conversion factors for units there. Okay, so here we go again. We're backing out again, a little bit larger view here, a factor of another 100 from the previous picture. So now the field of view is 1,700 light years. Okay, 1,700 light years. So 1,700 times 63,000, I mean, that's very large, okay, distance here. So now we're just starting to see thousands and thousands of stars here. Don't even think, I thought there might be an arrow for where our sun was. I don't see it on here though. But a representative picture of the part of the sky for a reasonable simulation here. But the sun and it kind of its neighborhood of stars, its local kind of area around it, its neighborhood. Okay. In that view, okay. Oh, and they mention here the gases and the dust that we don't see in here that fill in between the spaces of the stars. Now, these become very important. These clouds of dust and gas, because this is where new stars are born, out of that thin kind of cloud of dust and gas. Okay, so clouds of these did form, our sun about 5 billion years ago. That's a really good estimate, 5 billion years ago, when our star, the sun, was born. But yeah, so new stars are given birth in these clouds of dust and gas that really, are filling the space between our stars. So here we go, we're backing out a little further. Another factor of 100. And now we see a galaxy. Look at this beautiful spiral galaxy with the very delicate looking spiral arms. Now, not all galaxies, as we'll learn in our galaxy unit, not all galaxies have the beautiful spiral arms like that. There's a great characters in our galaxies, a variety of them. But the Milky Way galaxy, which is our parent galaxy, is a spiral galaxy, a barred spiral galaxy. And so if we were to place ourselves, our sun and our solar system, and where we would be in all these billions of stars that are in a galaxy, we would be about, 2/3 of the way kind of out towards the edge there. Okay, about 2/3 of the way from the center to the edge. That's where we would be located. So we're not the center of our galaxy. Okay, and it's kind of this idea that not only, but maybe 100 years ago, did we realize that, there's a universe full of galaxies. At one point there, we thought that our Milky Way galaxy was the universe, like an island universe, an island in a universe kind of thing. It wasn't realized that there's a whole universe full of galaxies. And even prior to that, it was thought that our little old solar system was the universe. So we'll go through kind of a historical side to astronomy and see how our line of thinking changed over time. But so here we are, we can see the Milky Way galaxy in this viewpoint, okay, and then that's where we are. So galaxies become a larger entity, okay, on our scale here. Okay, but this is our parent galaxy where we are. And there's the graceful spiral arms that we were mentioning. And so the visible disk of our galaxy is roughly 80,000 light years. 80,000 light years. So take 80,000 times your 63,000 AU, to get a perspective in there. Yeah, that's large. Okay. Yeah, and so we really didn't, about a century ago, didn't realize, that there are many, many, many billions of galaxies out there. Okay. And we're just one of many, many galaxies, many billions of galaxies scattered through the universe. Okay, and so now this view, here we are, another 100 factor increasing. So now that our diameter is 17 million light years, okay, in diameter. So here we've got an arrow on our Milky Way galaxy, our parent galaxy, and then you've got, some little clusters of galaxies, okay? And so clusters of galaxies get connected by a vast kind of network, but the clusters are grouped into what we call superclusters. So superclusters are clusters of galaxies, so clusters of clusters, but of galaxies, not stars, galaxies. So superclusters become the next. Okay, larger on our scale towards the large end here. So clusters of galaxy clusters in there, okay. And then these superclusters are linked to form what we call filaments. So kind of the walls that fill and go in and around and connect up these clusters in here. And the filaments are the largest structures in the universe. So filaments would be right here, yeah. So try to make a less than sign. So filaments. I hope you can see all of that on the board there, but I'm writing filaments, this word right here. Okay. So yeah, the superclusters kind of connecting together, filling all the little walls in there, and that's known as a filament. Okay. This has a diameter of 1.7 billion light years. Okay, in this view. All right, so really that has reached the limit of the largest telescopes on Earth. So if you were to go another 100 times, it doesn't even, our telescopes can't extend that far. Okay, so this is where our Milky Way would have been, that little red arrow there. Out of this sea of just supercluster walls and the filaments and the voids in between there. So very, very, very large. Kind of takes us to the end there. So trying to keep that proper sense of scale is going to be important for us. And we'll also kind of start talking about the origin of the universe and cosmology, where time scales become very important. We just mentioned that the sun was created and formed about 5 billion years ago. The Earth is thought to be 4.6 billion years old, and the universe is thought to be almost nearly 14 billion years old. So scale of time also will come into play. So we've got billions of galaxies that contain billions of stars. Probably some of those stars have families of planets, okay, like we have in our solar system. Some of those, it's probable that some of those planets would have a liquid water ocean like our planet does, the blue planet, that may have some nice atmospheres. Maybe they're in their Goldilocks zone, just right distance from the sun, and perhaps there are conditions for living organisms, even perhaps some intelligent life on some of these other planets. And it's kind of interesting to think about that. You know, maybe they're looking right back at us as we're gazing and looking out at the night sky kind of thing. So it's fun to kind of think about that as well. But yeah, so scale, very important. So kind of have an idea of what things are small and what things are very large on the scale of the universe. Okay, so that's done with that, but I do want to do a few examples of these unit kind of conversions that I talked about. That is one of the bullets, okay, on your study guide. So yes, we talked about scientific notation, the hierarchy of scale, so which objects are large, which are small, that's that, okay. And then know some units of distance in astronomy, which are more appropriate for certain distances. So when is it appropriate to use an astronomical unit? When's it good for a light year? And when's it good for a parsec? Then, you know, definitely trying to go between galaxies, parsecs are going to become important to us. But that last bullet, be able to perform unit conversion. So I have a few examples that we could pop under the camera here, just a couple, where we'll be using some of our conversion factors in here, you know, what they are, and then convert them into other examples in here. So, okay, different kinds of units in astronomy. Straight, okay. Yeah, so depending on what their work is, what they're doing, they might use a different unit, and they've introduced new units, as we mentioned. A lot of times they're going to use the sun as a reference. So they might talk about the radius of the sun. So that little symbol for the sun is a little circle with a dot in the middle. If we're talking about a solar mass, we always compare that to the sun, the radius kind of thing. So the sun is a nice reference. And sometimes you'll see that symbol there. Just wanted to interject that. On the small end of the scale, I know I have the really large units here, but there is a smaller end of the scale. The angstrom, the nanometer, and the micron, okay? When discussing the electromagnetic radiation waves, those smaller ones, so say a gamma ray or an X-ray, very, very small, ultraviolet waves as well, radiation, those tend to be on the smaller end of the scale. And then larger end of the scale, the astronomical unit, right? 1.5 times 10 to the 8 kilometers. An average distance between the Earth and the Sun, that's 1 AU. Okay. And then let's look here. I think I've got these up on the board for you, the light year. Okay. The light year, and I gave you a variety of things for the light year. Oh, and the parsec, yeah, we added the parsec in there. And then, like I mentioned, you can put a prefix on these, so a kilo parsec. 10 to the third parsecs, because a kilo is 1,000, right? Or 3.1 times 10 to the 16 kilometers, so that's a cumbersome number there. Unit conversions though, so we do want to make sense of this with the spectroscopy, so the wavelengths of things, the electromagnetic wavelength, versus say distances between a star or the size of a star or something like that. So this becomes important that we can convert between the units. And so I've got one example here. The speed of light is 3.0 times 10 to the 5th kilometers per second. And that's the speed of light for any of the light energy coming from the electromagnetic spectrum. It's not just visible light. It's any manner of light from the spectrum. But that is the speed of light in kilometers per second. So kind of cumbersome there with that number. And it takes 193 seconds for light to travel from the sun to Mercury. And so from this, we want to know what the distance of Mercury from the sun is. And so you'll do a little conversion. You'll set it up to where kilometers per second and seconds. So when you have that set up, so I don't know, I'll write it over here. Kilometers per second times second. So when you have units like that, you can see how that's going to cancel when you multiply through, and you'll be left in kilometers. Okay, so we're trying to set up and rearrange our calculation so that we can get the distance, the unit that we're after. Okay, so a very cumbersome number in kilometers, but if we were to write that in scientific notation, we get it into unity, right? So one digit before the decimal point, and then how many places did we have to move that? 1, 2, 3, 4, 5, 6, and 7. So 5.79 times 10 to the 7th kilometers would be that distance between Mercury to the sun. Okay, what that distance was. That was a little unit conversion. Here's just another one for good measure. And this next one. So 1 light year is the distance that light travels in 1 year. Our light year. That's our definition of our light year. And 63,000 AU. So that's, you know, in AU, 63,000. We also have it over here in kilometers there. But the light from the nearest star to the sun, which is Proxima Centauri, we mentioned, takes 4.2 light years to reach Earth. We did mention that earlier. From that information, what is the distance of Proxima Centauri from the Earth? And first off, we want that in AU. So if we have 63,000 AU, okay, which is 1 light year, so AU per light year, and the light years, that distance there in light years, okay, for Proxima Centauri to the Earth, okay, if we do that, and again it's AU over light year times light year cancels, and you'll have your unit of distance in AU. And so 264,600 AU distance, that's pretty big. Pretty big distance there of Proxima Centauri from the Earth. Okay. But now, what if we wanted that distance in kilometers? It's going to be a very cumbersome number, but we're going to have it in scientific notation. So for that one, we needed the 1.5 times 10 to the 8 kilometers per AU. 1.5 times 10 to the 8th kilometers per AU. We've already found what it is in AU, so we use that information from up there and bring it on down here. Okay, so that's kilometers per AU, and that's AU. AU cancels, and you're left with kilometers in your unit conversion. So 3.97 times 10 to the 13 kilometers, in kilometers. And so that's just a little playing around. You're given a unit, all the conversion factors I would give to you, so you don't necessarily have to memorize, those conversion factors. But so that necessary information would be given to you. But just, from your way your questions ask, what do they want that ending unit to be in? And then you'll arrange things, to make sure that they cancel so that you arrive at the correct unit that the question's asking for in there. So that's just a little bit on unit conversion. We'll have some little simple unit conversions for you on the exam, so you do want to make sure. So we have completed the first chapter there, and so we've met each of the bullets, so you do want to make sure that you've taken some good notes and can do all those bullets from chapter 1. You'll have your chapter quiz after this, so be ready for that, and definitely if you have any questions, as always here, any questions, make sure that you get with me right away, and I'd be glad to speak with you about this. Loves talking about astronomy. So until next time, bye for now.